Given 3 points on a 2D plane, can you instantly tell if they form a triangle or just a flat line? This is the core challenge of the valid boomerang problem. It sounds simple, but the trap lies in handling edge cases and avoiding precision errors. Let's see how to solve this with pure logic. You receive 3 distinct coordinates representing points. Your task is to return true if these points form a valid boomerang, meaning they are not collinear, and false otherwise. The catch is that valid boomerangs must form a triangle with non-zero area. If the points are distinct but lie on the same straight line, the answer is false. We need a robust way to distinguish between these two states without floating point ambiguity. The naive approach calculates the slope between the first 2 points and compares it to the slope between the first and third. If the slopes match, the points are collinear. However, this method is fragile. It requires handling division by 0 when points share the same x-coordinate and risks floating point precision errors. It also involves redundant checks for distinctness. While it technically runs in constant time, the implementation complexity and potential for runtime exceptions make it a poor choice. The key insight is to bypass slope calculation entirely and use the cross product from vector math. Instead of dividing to find slope, we calculate 2 times the area of the triangle formed by the 3 points. If this value is 0, the points are collinear. Mathematically, we take the vectors formed by the first point to the second and the first to the third, then compute the determinant. This involves subtracting coordinates and multiplying them. y1 minus y0 times x2 minus x0 minus y2 minus y0 times x1 minus x0. If this result is non-zero, the points form a valid triangle. This integer-only arithmetic is exact and handles vertical lines naturally without division. Let's trace this with points 1, 1, 2, 3, and 3, 2. First, we verify they are distinct, which they are. Next, we extract the coordinates. x0 is 1, y0 is 1, x1 is 2, y1 is 3, x2 is 3, y2 is 2. We calculate the vector components. The change in y from point 0 to 1 is 2, and the change in x from point 0 to 2 is 2. Their product is 4. Then, the change in y from 0 to 2 is 1, and the change in x from 0 to 1 is 1. Their product is 1. Subtracting 1 from 4 gives us 3. Since 3 is not 0, the points are not collinear, and the function returns true. The final output is true because the cross product yielded a non-zero value, confirming the points form a triangle with actual area rather than collapsing into a single line. You'll spot this pattern whenever you need to check if points are collinear or if 3 points form a specific orientation. Look for problems where slope calculation leads to division by 0 or floating point errors, indicating a need for the cross-product area formula. This solution runs in constant time since it performs a fixed number of arithmetic operations. It also uses constant space, requiring no additional memory beyond a few integer variables. Try the next problem involving polygon area or point orientation using this same cross-product pattern. Subscribe for more efficient algorithm breakdowns.